Okay. Hello, hello. Okay. Thank you. Hi, Brianna. Thank you for saying so. I love it. That is class participation right there. Hi, Brianna. Anybody else want to say hi? Hello, Danny. I love it. All right, now we're talking. Now we're rolling. So, hi, Brianna. Hello, Danny. Anybody else? This is not me taking attendance. This is me trying to interact with people as human beings. Oh, more people are coming. Hey, Amaya. Thank you. And I think I'm saying it right. And also, this is and no, that is actually true. Well, it is. Well, it's participation points. Absolutely, it is. It's also what I just expect after a while in my classes. But yes, and also this is also a way for me to try to make sure that I'm getting your names correct, which I'm still not in many cases. But so, oh, wait, and more people are here. Hang on, here we go. Believe me, it's extra. It's all about credit. So hi, Brianna. Hello, Danny. Hey, Amaya. I hope I'm saying your name right, or tell me if I'm not, please. Hello, Camilla. Hello, Jahim. If I'm saying it right, Jahim. Good afternoon, Jesse. I said, oh, I did say it right. Okay, great, great. Hello, Dahami. I hope I'm saying that right. Tell me if I'm not. But hello. Oh, and there's more. Hello, Enrique. Hi. Oh, this is what I got wrong last time. Jahara, I think. Hi, Jahara, I think. Tell me if I'm doing it wrong in the chat. And hello, Dahami, and hello, Amaya. And I think that's everyone. Let's see. Okay, yes, I think that's. And no, I do like the whole hello thing. Just it's cheesy, but it makes everything more civilized and human to me. And also, just so you, even though you're not going to really have me for much more, but it's not my way of taking attendance. I'm not looking at a roster of who isn't here. It's my way of interacting with whoever is here. I mean, if you're not here, I don't know who you are, but it's good to see you all again. Thank you for getting and responding to the message that we were online again today. Those people who responded to the message, yeah, you got 6 points for doing that. That was points right there, just because, again, that helps the whole communication and flow of all of this. It helps me know who, what's going on. So pardon me for, so let me say a couple logistical things here. Let me. Sorry. So one thing I'm just saying in the chat, and I will announce again, or we'll try to confirm again in Google Classroom, but this is our last session together online today. Again, it was like a 2-week situation where we have a lot of instructors missing overseas and things like that. And I'm very pleased to meet you all, and I'm glad to be together with you too. We might not go the whole time today. I mean, we might. We do have stuff to do. We're staying on track. We're going to do an online version of Lab 1 so that you're still staying with the curriculum. But just to be as clear as I can in the chat, it's saying as of next week, a week from today, you're back in the lab in person for the duration of the semester. You'll have Professor Lorwin joining you there. I'm very pleased that he's joining our faculty here. I've known him for a very long time. Very smart man, very smart man. Also, in addition to other things, also has a major background in film, which is, I mean, not like Hollywood films, but anyway, you'll have him as of next Wednesday. I will still remain in the background for all of this as a contact or as a resource to all of you for anything that might go right or wrong. in the class. So that's a logistical thing. Let me just also check one of the logistics. Pardon me for a second. And more people are still coming. And also I'll just say while I'm checking certain things, even when Professor Lorwin starts joining you and doing this lab piece of the course in person, he'll continue to use the same Google Classroom that we set up. He's already part of the Google Classroom, I believe, checking right now. And I will stay part of the Google Classroom. So we'll all be in communication. We'll all still know what's going on. And that includes Professor Liu, who's your lecture professor. We're all, I mean, that's one of the reasons I like Google Classroom. We'll all stay in the loop and know the right hand will continue to talk to the left hand. And all information will still be provided there in the Google Classroom. And yes, I do see he's. Now, one thing I just wanted to see very quickly, and I'm going to ask you a couple of questions in a minute. As I say, we are going to deal with Lab 1 today, but in sort of an online kind of way. I just want to see. Bear with me for 1 second. I'm sorry. Oh. Okay, terrific. I'm sorry. I'm just checking on. I know it seems like I don't exist. Okay. Okay. The one thing I'm checking right now. Okay, Ariana. All right. So I do see that Ariana's not. This is not me taking attendance. I'm a little. What I'm glad. As of now, every single one of you who's in this room right now at some point did get the message that we were meeting in this room, and you returned, even if it was 10 minutes ago, you returned the message, confirmed you, which I appreciate. So you just got 6 points. Some of you just got the 6 points right now because I was just checking. But every one of you who's in the room just got 6 points for class for homework, in addition to the points that you all got for having done game turn 1 from last week, which I very much appreciate. Again, it seems like we have communication. We're in the same system. We're in the same room. There's another game turn due tonight from today. When you do that, you get another 5 points, you know, and that will stay, all those points stay in the Google Class tallied at the end. And here is Ariana. Okay. So that's okay. Okay. So that's good. So thank you all. So that's how that works. So we're going to again talk today. I don't mean again. Today we are going to do our version of Lab 1, which really means what I'm going to do today. I'm going to walk you through some Lab 1. I'm not going to make you do it as such. And there's not going to be a report on it. And I'm going to look in the chat in 1 second. My main goal of today, by the time we're done today, and if it's early, great. But if it's not, it's not. But my main goal by the end of today is to have you fully in position to be ready and unsurprised when you come in to do Lab 2 next week. Okay, I'm going to look in the chat in 1 second. But so there's not going to be any new work or anything like that for Lab. Just one more game turn assignment that's due at 11:59 tonight. You know, the 1 second where you just write out the participation. There's not going to be any new work or any pre-lab or post-lab or anything that you have to bring for next Tuesday. I'm just going to try. We're all going to try as best as we can today to get ourselves in the right mental space to know what to expect when you walk in next Wednesday, to know what to expect that day, and to know I want to try to show you where it's all heading. The lab program for the semester. So basically our goal today is to get through a informal version of lab 1 just sufficiently so that there's no anxiety, so that there's minimum anxiety or stress or confusion when you walk in to do lab 2 next week in a new space with a new instructor and all of that. So that's the goal for today. And there's something preliminary, one last preliminary thing to get us there, but I just want to check in the chat. Okay. So we're going to turn our attention to what would have been lab 1. Before I do that, I think it's actually in all of our interests. And this part, again, today's a little bit informal, okay? And I do have stuff I need to get through with all of you. And I want, again, the goal is to make next week as livable and educational and calm as possible. That's the goal. So whatever amount of time that takes today, it takes. If we get there fast, great. If not, not. But to the one what will help me a lot and will help you through the whole course is, can I hear from you guys, voice wise or chat wise? Can you bring me up to speed about what you feel what's your I want to hear your description of what you think you're learning so far in lecture with Professor Liu. I mean, this is not a quiz. This is not a test. And of course, in the background, I know what she thinks she's teaching. I mean, I have the Google Classroom. So I'm not trying to put you in a weird spot, but I would love to hear what you're getting out of it, what you think the takeaways are. And especially if there's anything that you think you're supposed to be taking away, but you're at all confused or any questions, this would be, excuse me, a very good time for me to help you through that. Again, we have time today. This is informal, but I'd love to hear where you're at with lecture, what you think is going on. And definitely, if you have any questions or concerns, we can address them right now. So, okay. And again, this is informal. So I'm looking into chat. Okay. And thank you, Ariana, for answering already. And please, everybody understand, like I'm about to start reading Ariana's answer, which I appreciate. There's no redundancy here. Even if 3 of you all, it's not a race either. So, and you are getting class participation points or whatever. Even if 3 of you say the same thing, don't worry about it. That honestly, in fact, if all 7 of you said the exact same thing, that is different from just 1 of you saying it. Then I know it's like 7 times true, if you know. So please, all of you, don't hold back. I really want to know what you think is going on in lecture, and I want to know what you're concerned about. So it's not a race. I'll read everything in the chat, and don't worry if someone else like beats you to it or something. So okay, so I'm going to start reading right now. But thank you already, Ariana and Brianna, for answer. Okay. Oh, right. Oh, okay. Oh, wait, this is very helpful. Okay, I like the way you're putting it. Okay. So you're like building up review. Okay. And actually, this really helps me. I'm going to ask some more specific, because already I could see that. Okay. So you're thinking about sines and cosines. And yes, of course, that's a math thing, but yes, we're totally going to need it in this physics course. And you're even comparing the slopes of cosines and sine functions. Oh, that's very good to know. Let me ask a couple more questions. But again, and anybody else, by the way, this is a discussion, even if it's in the chat. Anybody else? Cool. Like, thank you, Danny, so that did add information, what Danny just did. And if any of you even just wrote like confirmed or agreed or facts or whatever people say, or that weird caret thing that even if you do that, even if you're just like, yeah, I agree with Danny or I agree with Ariana, it really helps me. Okay. Like this class like has different moving parts, it has lecture, it has lab. They're all meant to be communicating together. The more and you have a funky start to the year. So the more we can all be on the same page, the better it is for everybody. So, okay, so please feel free to chime in just like I agree or I don't agree or whatever. Generalization of cosine and sine expressions. comparing the slopes of cosine and sines. Very good, very good. And yes, that is totally true. To add, oh, we incorporated rate of change. Very cool. And yes, that does help. And yes, and I didn't know you did that. I mean, I knew some of this, but I did not know that. So you actually looked at slope and rate of change on sines and cosine functions. Good. How sines? Okay, it was pretty. Oh, and that's fair. By the way, what Ariana, sorry, did I read? How cosine and sine affects the appearance, like the vertical and horizontal axis. I think I know what you mean by that. That's good, Enrique. Thank you. And what Ariana's saying, her honesty saying, it was clear at first and then got weird at the end. She didn't say weird. I'm saying weird. That's very helpful to me. And if nothing else, believe me, again, if we have a moment, if we want to get to the piece where you think it started getting confusing, I'm here to address that. I mean, please remember also, it happens that I'm not teaching the course formally this semester, but I have been the lecture instructor for this course for years. And Professor Liu used to do it too. I mean, she's done it before, but I'm here to help. So we went, and you did go back to Hooke'sLaw. That was going to be my next question. You used decimals. You use decimals. Okay, great. Oh, this is very helpful. I'm very glad to know. Oh, okay. Oh, you got a lot going on. This is great. So you've actually answered. I was going to ask, so did you apply any of this raw math to physics? And it sounds like, yes, you did. Okay, very helpful. Let me ask. And also, don't think that you're making class longer by answering this. The more you're telling me about this and the more we're talking about this, the less I'll have to say about lab one, honestly. So you're not adding, you're helping your own efficiency. You're not making class any longer by participating. So I got a couple more questions on this. This is great though. Thank you, Brianna. Thank you, Ariana. Thank you, Brianna. Thank you, Ariana. Thank you, Enrique. Thank you, Danny. Thank you, everybody. A couple more questions I have about this. One, maybe I have three questions. One, when you say about rates of change and slope and stuff like that, could anybody have, at the risk of putting anybody on the spot, does anybody have the confidence to be a little bit more specific about that? Like, did you come to some kind of, you say you compared the slopes of the sine and cosine function. Did you come to any kind of conclusion or takeaway about that? Is there any finding that you could, oh yeah. Is there any, like, what do you feel that could be said about the slope of the sine function compared to the slope of the cosine function? Or is that too weird of a question? Maybe that's too weird of a question. Well, okay, I'll give it I'll say this. This is when I think of comparing the slopes of the two, what I think, tell me if this jibes with what you were learning or if it seems consistent. What I think about the slopes is wherever, okay. Oh yeah, take your time. No, take your time, everybody. Yeah, if you could have your notebooks out for this for lecture, that would help a lot. And this is not a test. I mean, I'm not asking you to have memorized anything. I mean, no, I kind of want to know what's in your notes from the other day. Actually, that is what so please do find your notebook. And I'll pause for a second. I'll start to say, well, all right, okay. Oh, good. Wow, okay. That's great. Hold on, I'm seeing what's in the chat. And I'm glad Ariana's getting a notebook, but yeah, that is great. What Danny has written, the rate of change of the sine function is cosine. What Jesse has written, the rate of change of sine is the cosine function. That's beautiful. And the rate of change of the cosine function is the negative of the sine function. That, first of all, definitely correct. What Danny's saying, what Jesse's saying, definitely correct. Also, the way you're putting it, I don't know if you're copying that straight out of your notebook or that's like in your head, but that's a very good, precise clear way of putting it. Like it does feel like you guys learned something here. We learned different values affect the rate of change. Oh, wow, great. Oh, and the B and the A, like in decimals. I'm reading Brianna's thing. Okay, this is great. You're for a class that's starting off this chaotically, you guys are certainly not behind. I mean, I don't know if you care, but this is great. You highlight them in. Great. Okay, so forget this page. I was about to start, but you've answered. That's great. Hold on. Okay, I don't even have to do what I was about to do because you just did it for me. This is great. Okay, I agree. If there was one takeaway that I was going to make sure you had from sines and cosines, I definitely agree. It's what you said. Like the cosine graph itself is a graph of the rates of change or the slopes, or if you like calculus, the derivatives of the sine function. Totally agree. I agree that that's true. And I agree that that's a big takeaway. So good for you guys. And conversely, if you look at the cosine function, if you look at the rates of change of the cosine function, you find that they are the negative of the sine function. That's right. Derivatives, yes. If you're familiar with calculus, these are derivatives we're talking about. Absolutely, that's awesome. Okay, I think you guys really know something. And now I'm going to ask a dangerous question, and then we're going to use this to segue to what we have to do or talk about in terms of our first lab. How, and you definitely get it. Oh, well, and again, if Ariana remembers, or if anybody remembers where things started getting confusing by the end, you're invited to let me know and I'll try to address. But maybe it was confusing enough that you don't know how to say what is confusing, and I can understand that. Let me also say I'm very pleased that you've already dealt with Desmos. That gives you a huge leg up. That was half of what I needed to talk about today for your to get you prepared for lab 2. So if you guys feel somewhat comfortable or familiar with Desmos, it sounds like you're saying you do. That's terrific. I mean, I think that is what you're saying. So I have one last question about this. How does any of that cosine sine stuff, what does that have to do with f equals negative kx? Like, maybe this is an unfair question. I don't know, but what does it have to, I'm just turning back the page. What does that have to, like, yeah, what does that have to do with f equals negative kx? Or what is f equals negative kx? Yeah, I'm going to add, because I'll be, okay, let me be as straightforward as I can also, so you don't think, oh, great, yes. And thank you, Jahim. Yaverbound. Jahim. Hook. Yes, f equals negative x is, f equals negative kx is Hooke's law. And let me tell you right now, that would have been a big sort of takeaway or conclusion of lab 1. So what's terrific is if you've already seen it with her, you're saving us a lot of time today. Maybe we won't be here the whole time today. I wouldn't be upset with that if that's the case. So now if I'm going to ask you a couple of questions about Hooke's law, please understand it's in service of what we would be talking about in terms of lab 1 is really supposed to be about Hooke's law. My goal is to make sure that you're okay with Hooke's law before you move on to lab 2. Sounds like we're already part way there. So okay. Okay, I'm going to ask, so I'm going to tell you right now, again, the purpose of lab 1 would have been to establish this law. It seems that you've seen it, so good, but let's make sure can you tell me a little bit, like, yes, Hooke's law is F equals negative KX. And I'm going to tell you that that's a law that applies to all springs, or at least all good springs, all well-behaved springs. In fact, I'm going to go a step further and say that really this law, this Hooke's law, it applies to all springs, but really what's important about it is that what it really does is it applies to all springy materials. This is really a law that not only governs or applies to, but in fact kind of defines what we mean by elasticity. Okay, an elastic, so I'll write that. An elastic material is a material that acts springy. Material that acts springy is material that acts as though it was made up of lots and lots of little springs, right? Now we're studying in this class for a little while little coils of metal that we call springs, and we're like talking about how they behave, but they can seem like a very obscure sort of weird piece of equipment to get so obsessed about, unless we realize that by understanding a little spring, what we're really doing is we're understanding springiness in general. We're really studying what it means for something to be bouncy or elastic, because it turns out that in nature, tons and tons of systems are elastic in this way, even if they don't necessarily look like they're made of metal or coils or anything like that. Like lots and lots of systems are elastic at the atomic level, where we wouldn't even see any metal or any coils or anything like that. But any system that ultimately behaves elastically at all will apply all the properties and consequences and behaviors that we investigate in a particular spring. So this is a long way of saying we're going to be studying springs for a while in this class, ultimately because we're trying to ultimately study a type of motion that springs undergo called harmonic oscillation. And that is because that type of motion underlies a whole bunch of really important systems in the world, not just coils of metal. We'll get to that. But so this fundamental law, the definition of elasticity is this Hooke's law, F equals negative KX. I'm also going to say, so please take note. So I'm starting to talk right now. I apologize. F equals negative KX is what an ideal, a perfectly well-behaved spring would obey. The worse the spring is, the less it perfectly obeys this, but the better the spring is, the better it obeys this. What does it mean to be a good spring? What it means, we don't have to have a perfect spring to really manifest this behavior, but what it means to have a really good spring is a spring is something that you can stretch and compress, right? A spring, I mean, I think you know this, like if you picture one end of a spring being fixed to like a wall or hung from a ring stand or something, the other end of the spring can be pulled out or pushed in. You can imagine a mass being affixed to the other end of a spring, and the mass can be pulled to one side of the spring's generally relaxed equilibrium orientation, or it can be pushed to the other side. Wherever the edge of the spring normally is, we call x equals 0 or equilibrium, and we're assuming in general that the edge of the spring, if you leave it alone, it would be at x equals 0, but that you could stretch it to one side of x equals 0, or you could push it in, compress it to the other side of x equals 0. The bigger the spring is, the longer the spring is compared to these extensions or these compressions, the better the spring behaves. Okay, that's the bottom line. Is a well-behaved spring is one that is being extended or compressed small amounts compared to how long it is. So, so the longer a spring is, really the better. Conversely, the less you try to wiggle it, the better. if that makes any sense. Now I'm going to pause for a second. I'm going to go to the next page. Okay, so in this F equals negative KX law, X is a displacement measured in meters from some equilibrium position, whatever the equilibrium position is called X equals 0. X can take on values to one side or the other of 0. So X can take on positive or negative values. And also, okay, sorry, this is getting a little illegible at the bottom. What I've written at the bottom that you probably can't read, what I've written in blue at the bottom is X, displacement from equilibrium position, refers to the edge of a spring, like this whole idea of a spring, whether the spring is horizontal, as it often is, or vertical, as it will be in the lab for a while. Whether the spring is horizontal or vertical, what we're assuming is that one edge of the spring is fixed. And the other edge is one end of the spring is rigid, and the other end is affixed to some mass, M, and it's the mass that moves back and forth. We pay attention to the mass. It's the mass whose motion we track or we observe or we measure, excuse me. And whenever the mass just sits there happily, naturally on its own, that position of that edge is what we call 0 and all other. So it's the edge of the spring that we're measuring relative to some 0. I mean, that's probably clear to most of you, but I'm just trying to establish. So that's what we mean by X on a spring. Now I'm going to stop and I'm going to ask you now, what do we mean? So you saw this law already. That's great. What do we mean by F? What is F? Well, one second. Sorry. Okay, chat. Cool. You guys are. I just want to check. Great. Okay. Ooh, and great. I totally agree. Thank you, Vonnie. Thank you, Jesse. Thank you, Brianna. Yes, it's the force of the spring, and I'm even going to say at the thank you all three of you. You're totally all three right. I will admit that I do particularly like Brianna's phrasing. I like them all. I like them all equally. You are all my children. But yeah, force exerted by the spring really sings to me, because I always like, whenever I think of force, I always like to think of force as an interaction between two objects. A force is always, this is just a reminder to everybody, or just perspective, force is always in physics something that one thing does to another. right? As opposed to say like temperature or mass or even maybe velocity, which is something that an object has. Like an object can have a temperature, an object can have a mass. We could talk about the mass of an object. We could talk about the temperature of an object. But, and again, I totally agree with what all three people put in the chat. But to be technical or to extend this, I like to think of force. I mean, I don't like to. A force is something that one object does to another. So yes, the F in this case is the force exerted by the spring onto the mass. It's the force exerted by the spring onto the mass. That is totally what force, what F stands for here. Yes. Hold on, just. And of course, it's measured. So, and it's measured in newtons. Yes. Now I'm going to pause right. Of course, I want to talk about the K. You probably already did. And I want to talk about the negative sign. But I'm going to pause right here because, of course, I'm not the lecture instructor. It's like my job to help us navigate through the lab program. So I'm going to, assuming that much, it seems like that much is clear to you guys. And again, good. Like, what does this have to do with the lab or the first lab or whatever? I'm going to tell you. So I'm going to turn again. I know that I haven't addressed K yet or the negative sign. I'm kind of thinking it seems like you probably know because you're all such good people. But that alone, I'm going to turn to the next page and say, okay, I'll explain this. So what I'm now about to tell you is like what would have happened in lab one. And the kind of thing that would have happened in lab one is what's going to happen in lab two, just with different mathematical details. I'll explain in 1 second. Okay, sorry. I was actually just, that was your lab instructor communicating with. Okay, so here's what would have happened in lab 1. And this is, well, I'll read, you probably can't read my blue handwriting. What it says is you would have walked into the room, found a bunch of equipment on your table, and you would have seen something like the following written on the board, on the whiteboard in the room. You would have seen something like F squiggly symbol X period T or F. Okay, the squiggly symbol between the F and the X is a lowercase Greek letter alpha. I'm going to find out for you. Some of you might be familiar with it. Some of you might not. We'll talk about it in a second. That's part of my goal here. But you would have seen that on the board. You would have seen a bunch of equipment on your lab tables, and you'll have lab groups and all of that. But you'll see a bunch of equipment on your lab tables. You'll see a statement on the. You would have, and you will always in the future see one statement or two statements or three statements on the board. There will be some sort of equation or proportionality like this one, and then it'll say true or false. Okay, now I'm going to let me stop me if any of this doesn't make sense. Again, I'm telling you what would have happened in lab 1 so that you get the general routine down and understand like what to expect for lab 2 and all future labs. Okay, first thing I want to say, so I'll even write this on the next page again. Okay, first thing I want to establish is that I'll say one other thing. Okay, some of you may, well, let me ask this actually. That symbol that I'm using right at the top of the page here, that sort of looks like a fish, which is actually a lowercase Greek alpha. Can I just ask, some of you may have seen it before, but did Professor Liu use that symbol at all in any of her discussion? Or has that been introduced or used in lecture at all? And there's no right or wrong answer. I just want to know. Not yet, I think. Okay, that's fair. No, okay. I totally believe you. It's totally very possible that she is not. Okay, not yet. And thank you. And welcome, Shio. Great to see you. Okay. Thank you. Okay. So I'm telling you all now, you may have seen before in another class or may not. What it means is directly proportional to. It will come up a lot in lab, certainly, even if it doesn't come up in lecture. It means directly proportional to, or varies proportionally to, or varies linearly with. Okay, and direct proportionality is a huge concept in science, as you know, and a huge concept in math. And I know you've in some ways been studying direct proportionality like for years. In some ways, we all know what direct proportionality is, but I also want to caution you and welcome you to admit to ourselves, in some ways, people go through their whole lives not fully knowing what it means, partly because we all know what it means enough that what ends up happening to many of us is we end up thinking that anything that's at all related to something else is related to it proportionally. Like the best way to know what direct proportionality means in a way is to have in our head at all times the difference between something that is directly proportional versus something that isn't. Okay, and that's what we're going to kind of be studying, especially in lab number 2. But it does mean is directly proportional to, and in mathematical terms, one way to understand, well, there's two big ways to understand what direct proportionality is in math. One is that if something is directly proportional to something else, that doesn't mean that it's equal to something else. It does not mean that they're equal. Like, that's why we have a different symbol. If I say F is directly proportional to X, that doesn't mean F equals X. But it does mean that F equals some constant number times X. And whether I know what that constant number is or not, for something to be directly proportional to something else means, for one quantity to be directly proportional to another quantity means that one quantity equals some unchanging value times the other thing, whether or not the unchanging value is known. The important thing is that that value doesn't change. So that's one way to understand direct proportionality. But another way that comes up all the time, another way is where you've seen this before, and some of you, this is like really, really old news. I know that, but others of you, it might be old news, but you never thought of it in this way. When we say direct proportionality, what we really mean is that if you made a graph of one value as a function of the other, that you would find the graph to be linear. It's like to say y is directly proportional to x is to say that y equals some constant value called m times x, even plus a b. B does not have to equal 0. What, like, how am I relating to? What am I saying? I'm saying that as long as runs in the x value, as long as changes in the x value always yield the same amount of change in the y value, then that's what we mean by direct proportionality. And what that means is if we were to put things on a graph, we would have a graph that had an unchanging slope, right? Like, slope is rise over run. It's change in the y value per or divided by or versus change in the x value. So to say one thing is directly proportional to another is to say that the way that one changes relative to the other is always the same. It's to say that we have constant slope. So direct proportionality means, and I know, again, I apologize, I know a lot of you know this. I'm just trying to review it in our terms, and I'm trying to put it, partly I'm just trying to define a symbol, but I'm also trying to put this in concrete terms because, again, we're going to sort of really need this in the lab. So just to make sure we're on the same page, I apologize if this is really, if it's old news or boring or whatever. So when we say that one measurement or one quantity varies in a manner that is directly proportional to another measurement or quantity, then we're saying that if you put one on a graph with the other, you would get a straight line, not necessarily a y-intercept of 0, right? Just a straight line, a line whose slope is constant. Let me also rush to point out the slope could be anything as long as it's constant. So the slope itself could be positive or negative. Like, just to be clear, just to be totally clear, especially because I think you could see that this is sort of, if we're relating this to springs and stuff, like, if that's a straight line, even though it's got a negative slope, even though it's going down, and even though the y-intercept is not 0, that is still a direct proportionality right there. Okay, any kind of curve. So like y equals sine of x, y is not directly proportional to x, right? I mean, it's definitely related to x in a very direct and simple or predictable way, but y equals sine of x or y equals cosine of x. You might even want to write this down. Maybe I will in a minute. Those are not examples of direct proportionality. Frank, just simply put, because the graphs are not straight. Okay. So from here on in, if you're told that something is directly proportional to something else, that means that something is equal to a constant times something else. Now, if you had walked into the lab today or last week for lab 1, you would find a bunch of equipment on your table, and you'd find this statement. Okay, again, what I'm writing right now, which I'm asking you to write, I'm sort of scrawling it out. I realize what I'm writing right now, I'm not asking you to do right now. I'm telling you this is what would have happened in lab 1, and I'll tell you the answer and stuff like that. But again, I'm also telling you that something very similar to this is going to happen in lab 2. And some of you may find this unusual, this kind of approach to lab. Some of you might not. Some of you might at first find this kind of approach to lab frustrating. Some of you might not. We're hoping in the long term you find it very unfrustrating. And again, depending on who you had for 101 or where you did 101, maybe this is old news, but maybe not. What I'm saying is, in lab here, you don't get a recipe or a step-by-step cookbook of how to do labs in 102. What you get is a goal, and you get equipment, and you get a guidance, and then you're on your own to design and test and conclude. Now, of course, you have a lab instructor, and you'll have a lab tech walking around to answer questions and to help you and to keep you on track and all of that. But specifically, so for lab 1, what would have happened is on the board, you'll get this statement: F is directly proportional to X. Now, again, I think many of you hopefully maybe at this point already know the answer to this because you've had lecture and stuff now, but you get a statement like that where you might not have had the lecture yet. And the statement is a somewhat more general statement even than anything you'll see in lecture. Like, you notice this statement is not an equation. It's a relationship. It states that F force is directly proportional to X displacement for a spring. And you'd see that on the board, and it would say true or false on the board. And then you'd walk in and you'd have this equipment provided, expected equipment like springs, rulers, ring stand, stopwatches. Although, frankly, I will tell you right now, any experiment that we do, including definitely lab 2, anything where we provide stopwatches and stuff, I'll tell you right now, you're not only allowed, but you're encouraged to just use your own iPhones or phones instead of our stopwatches. First of all, our stopwatches have now been sitting for 2 years of COVID, and I think almost every one of them is dead. Of course, we're going to fix that situation, but I don't know how quickly we can. But number 2, we found even before COVID, the truth of the matter is, these days, everybody's phone is a much, much better piece of equipment than any stopwatch we have in the lab. So you're always welcome to use whatever equipment you happen to have and rely on. Anyway, you'd be given a bunch of equipment, stopwatches, ring stands, spring scales, iPhone, laptops. We have a cart full of laptops and iPads that have Desmos on them. And so I'm very glad you've already looked into Desmos. They also have Excel, or many of them have Excel. If you prefer Excel, also many of them have this program called Logger Pro, which many of you might have used in Physics 101, or if you came from a different college at a different college. Anyway, you'll get a bunch of equipment and you'll get this statement, or sometimes more than one statement on the board. And your goal is to design and execute an experiment or a data collection procedure that will enable you ultimately to establish whether the statement is true or false. Okay, so it's not totally open-ended. You're not just like flailing, and we're not just saying figure out something about springs. We're telling you something specific that is either definitively correct or it's definitively incorrect. And that will direct your attention. But your goal is to find out whether it's definitively correct or definitively incorrect. And you're going to do that by collecting a bunch of data according to a procedure that you design. And then I'll even say this right now. Whoa, oh, I just lost the board. And that probably just all got erased. Hold on, sorry. Ah, okay. It's coming back. Should be coming back in a second. Too many devices using Wi-Fi here. Okay, it's coming. Okay, there's more. I'm going to stop for a second so you can copy that down. I'll read it out loud in a second, but I'm going to give you a second to copy that down.
Four players in Donchen Band. Or face off against.
Pardon me for one. Hold on. Pardon me. I'll be right back. Just 1 second. Okay, so sorry. Oh, wait, are you still there? Okay, so sorry, family. Okay. All right, there's more coming to this, but so I'm going to say, so the idea is that lab is up to you. There's always a goal in lab. The goal is for every lab. You guys are still right. Sorry, it's because I just left for a bit, which is totally my fault. But can I just can you just verify in the chat if you're still with me, if everybody's still here? And great. Thank you very much. Thank you, Shion. Okay, great. That's good enough. Thank you. Oh, thank you. I like the yes, sir. Oh, sir. Great. Thank you all very much. Thank you, Danny. Thank you, private chat person. Thank you, Jesse. Thank you, Enrique. Thank you, Amaya. Thank you, Brianna. Okay, great, great. Thank you. And I apologize. And again, I'm trying, believe me, I'm trying to get you out of here early if I can. And thank you, Vani. Awesome. Okay. So I'm saying when you walk into lab, there will be a statement or a couple statements on the board. They'll be super relevant to everything we're doing. They will be what you're trying to figure out. They're not true. And thank you, Ariana. Awesome. But they will be either true or false. That's sort of the goal of each lab, is to find out whether they're true or false. That's the sense in which it is an experiment. Like, we're not giving you the answer, but we are giving you the type of answer. So then your job is to take the equipment and design an experiment yourself to figure out whether that ultimate answer or that ultimate statement is true or false. Now, it's not nearly as, I don't know if that, so it's not meant to be a trick. Like, we will write something on the board that sometimes is false. We're not trying to trick you. We're, it's like a hypothesis. You're testing a hypothesis and finding out whether it's confirmed or denied. And when we say you have to design the experiment, believe me, we're not saying, like, it's not invent the wheel, and it's not, oh, you're totally in outer space with no guidance and you just have to, like, we're expecting you all to be Newton and Einstein and Galileo, like making up things for the first time. No, the statement that's on the board will be some sort of relationship between some sort of dependent variable and some sort of independent variable. And so in a way, once you get used to this, or once you get used to sort of basic physics experimental design, it's more or less like the same type of thing each time. Like, you'll get used to what you're trying to do and how to do it. And the basic idea is this: like, for each lab, first you create a 2-column table of data. In the first column would be the independent variable. The second column would be the dependent variable. In this case, in other words, presumably, maybe I don't want to give away the farm, but in this case, presumably X is the independent variable measured in meters, and F would be the dependent variable, because F here either is or is not a function of X. So you set up a 2-column table of data that could be in your notebook or on your laptop or whatever. Then you're going to create a procedure for collecting data. That's where, you have to think a little bit, where it'll be a little bit different each time. But the way to collect data is to test different values of the independent variable, presumably in as close to regular intervals as you possibly can. I also just want to say, let me look in the chat. What's it? Oh, okay. So you're going to set up some sort of procedure for collecting data, which really means trying different values of the independent variable, ideally trying them, trying different values that vary by regular intervals of the independent variable, and then finding out what value of the dependent variable they return. Now, in many of the labs we do here, the equipment is somewhat primitive. The situation is somewhat primitive. So it's not like you can collect 1 million data points. For example, in lab 2, the one that you're going to do next week, it may not be possible to test for more than 5 or so different values of the variables for next week. You're trying to get about 5 different data points, not much more than, I mean, more is better, but at least 5, like 2 or 3 is not sufficient. I will give you a hint for right now, for all time and including next week. When I say that you want to collect 5 different data points, one data point that often is a data point in labs, but not always, one data point that's almost impossible to measure, but often exists, is the data point 0,0. It's always good to ask yourself in any experiment that you set up or in any data collection procedure that you initiate, it's always good to ask yourself, do I think if the independent variable had a value of 0, would the dependent variable have a value of 0? Or even better, you could just ask yourself, if the independent variable had a value of 0, do I know? Could I imagine in my mind without doing anything what value would be returned by the dependent variable? Now, sometimes you don't know, and sometimes it's not 0, 0, but and often you can't measure this one. Like a value of 0 is not something you can measure, but often you can absolutely picture in your head what would happen. And for the case of 0, you're not allowed, not only are you allowed to do that, but you're heavily encouraged to do that. If you have reason to believe that a value of 0 in the independent variable would return a value of 0 in the dependent variable, then it's very, very advisable to write that down. If you believe it at all, if it's seems roughly convincingly true, then it's probably very precisely, definitely true. If it's, in other words, 0,0, if it's a value at all, it may be your most reliable and most instructive value. So always, it doesn't mean it's always. Let me say that again. You might want to write this down. If 0,0 is a value at all, then it's probably your most precise and reliable value. So it's always important to ask yourself when you set up a data collection procedure and a table of values, always really good to start by just asking, do I think 0,0 is going to be in this table? If not, then no. But if yes, then it's like super important value. Okay, so you create a 2-column data, a 2-column data table. You create a procedure for collecting data. That's sort of where your thought and discussion and maybe time will come in. And everything I'm saying is within lab groups. You'll have lab groups. You're not doing this on your own. But the lab groups will be small because it's a small class. And also because we can't sit that close to each other in COVID and all that stuff. Right? So you're going to make a procedure that can involve some creativity, that can sound intimidating, but it's also somewhat straightforward in the sense that a procedure means, how can I, well, I'll turn this to you guys in a second, but like in a case like this, you're trying to test whether F is directly proportional to X. So you would try different X's and test to see what F occurred. And ideally you would try an X of 10 centimeters and then try an X of 20 centimeters and then a 3 or something like that, right? And again, we could get into the more of the details of exactly what I mean by trying these values. But the thing is that if the main thing that makes an experiment, the main thing that makes experimental design good design is that every time you vary the X to try a new value of X in order to find out what value of F occurs, you want to make sure not to vary anything but X. I mean, that sounds obvious in a way, but sometimes that's easier said than done, or sometimes it's easy to not see that you're not doing that. So hold all other things fixed besides the one variable that you're deliberately tweaking. Anyway, so you do that. We're almost done with this. I know this is super boring. So it says, follow your own procedure and collect data, always making a conscious point to vary as little as possible other than the independent variable. Okay, then 4. Okay, we're almost done with this. So you get your data. Again, collecting the data is really the part that takes the most creativity or the most thought. And you might take some time with your group to figure out how. But the whole experiment means create a table of values, and the table of values is always a 2-column table when you really think about it. There might be more than one goal in a lab. There might be more than one statement you're trying to verify. There might be more than one relationship, but each goal itself is a relationship between two variables, no matter how complicated it looks. Even if you see something on the board that has a lot of other letters, all the other letters besides 2 are constants. Like, we're always in the lab testing how one quantity varies in response to another quantity. So it's always a 2-column table. You get the data in the 2 columns. Maybe you'll only have like 5 entries in those columns. Then you create a scatter plot always from those 2 columns. And again, I know that all of you essentially know all this. I'm not, but I just want to make it clear. So then you make a graph where the independent variables on the x-axis, the dependent variables on the y-axis, and you plot the points. You're welcome to do this by hand. So, I mean, you're welcome to do it by hand. Some people feel more comfortable doing it by hand, or you're welcome to use Desmos, especially now. I'm very glad that you've had some practice with Desmos. So I highly encourage you to use Desmos. Some of you have used Excel before to do this. You're welcome to do that. You can do other programs too. You can even use Logger Pro in the laptops in the lab. You will be given laptops and iPads in the lab, but of course you can also bring your own. If you like other programs, you can use them. I think the best way really is Desmos or Excel or hand, but whatever. But you make a scatter plot, and here we're almost done with this dry discussion. But I want to emphasize: pause after the scatter plot. Like, make a scatter plot. That means just the dots. Make a graph of just the dots. Make it as big and clear as you can. Choose your scale your axes appropriately. Making the graph is never exciting. People, I know generally at this stage people hate making graphs, but it really is the sort of key undertaking of any experimental procedure. It will take you time. It is what lab time is for. So don't rush it, and don't feel like you're behind if you're taking time doing this, but you need to make a graph. Making a graph means the dots, the raw dots, the scatter plot. Then, and stop me if you want me to go back a page. Okay. This step that I'm on right now is kind of the most important step. It's the one I'm going to dwell on a little bit. Then I'm going to bring this all back to F and X, and then hopefully hopefully we'll probably be able to wrap up. Hopefully, I mean, we still have an hour technically. We still have an hour. I don't want to. I'm going to try. Anyway, I keep saying that, but just bear with me. Again, the goal here is to have as few surprises and as little stress or anxiety when you walk in next week. So I'm just trying to give you whatever I can give you so that that happens. I'm going to say now, but please stop me if there's any questions so far. I'm going to say you walk into, so you make the labs is what we're really saying. Okay, you design the labs. We don't design them for you. We tell you what it is that you're trying to establish by the end, and whatever it is that you're trying to establish by the end, we do mean by the end of that period. Okay, everything that you're doing, all the steps that I'm describing right now, you're certainly taking notes and writing down in your own lab notebook or in your own laptop or whatever. We don't collect all these as such. You're writing these out the way you want. There are lab reports and there are ways that you become accountable to this later on. I mean, so keep everything clearly, but you're not literally going to hand us a formal procedure or anything like that. You're making a procedure that works for you. We'll know in the end whether it worked or not when you get to the conclusion. Okay. So this is the like researchy sort of. So we have the statement on the board. You create a 2-column data table. You create a procedure for collecting the data. You collect the data. You put the data together into a scatter plot, which means just the raw dots. Okay. And then you pause and you sit back with your partners and with other groups if you want, and you look at those dots. And this is where you put thought in. This is where the true science of science comes into play. And this is where science, the better we know science, the more it actually ultimately resembles an art form, because this is the moment that is not algorithmic or procedural. This is the moment now that cannot actually be done by a computer, even though many people mistakenly believe that it can. This is the moment where you look at your dots and you try to come up with the simplest, smoothest, best model, shape, pattern, trend that actually captures those dots. This is where you try to look at those dots and infer what type of relationship the dependent variable bears onto the independent variable. This is the real part. This is the science part. And in some ways, this is the hardest part to learn and to teach. And in some ways, this is the part that some people get better at than others. And that's what makes them better scientists in a way. And it's the part that feels the least scientific at first. So what I'm talking about is that you get a scatter plot. And what I'm talking about is, yes, I'm talking about getting what you might consider what's sometimes called the best fit line or the trend line or the model fit or the best fit, like whatever those terms are that you know, that's what I'm talking about. But I want to be very careful about this. All graphing programs, I mean, including Desmos, including Excel, have various buttons and various functions or various tools that will spit out a best fit line or something like that. And you will take advantage of those, but not at this step, not yet. Let me be clear what I'm saying. Okay. Let me be very clear about this. So you're going to come up with the idea of what the best fit is for your dots. The computer's not, you are. First of all, so the best fit is supposed to be the shape that most accurately, the simple, smooth shape that most accurately captures the pattern of the dots in the scatter plot. Now, again, of course, the more dots you have, the more visible a pattern will be. But this is where this gets nuanced, and this is really where science is science, where it's not quite math and it's not quite art or something. What I mean is this. Necessarily, the way the dots came from the experiment, the dots will definitely not fall into an exact pattern. The dots will be approximate. They will have uncertainty and error associated with them, as you know. So the dots will almost definitely not form an exact, smooth, perfect pattern. What we are looking for is a smooth, perfect pattern, right? We are ultimately looking for a mathematical function that most accurately resembles the non-mathematical reality of the dots. So first and foremost, what we don't want to do is play connect the dots. We are not looking for some etch-a-sketch, some sketch that actually hits every single dot. Any way you would, like, that is something that sometimes people care about, but not in science. If you connected all your dots with like line segments, there's no way you would get a smooth, simple pattern, because there's no way, unless you're lying, that your dots actually fall into one smooth, simple shape. So we're not talking about connect the dots. Our goal is not even to draw, anything that actually hits all the dots. In fact, our goal is to draw something that probably hits none of the dots. Our goal is to draw something that is a smooth, simple, recognizable shape that might be a straight line, but might not be. I mean, it should be a smooth, simple shape, like a straight line could be the case. I mean, it could be a horizontal line, that's unusual, but could be a diagonal line, unusual, but could be. If it's not a diagonal line, it would be the next simple thing, like maybe a parabolic curve, like a parabola, right? Or maybe it's a curve like sine and cosine, or maybe it's a curve like y equals x third to the third, like a cubic, but not a random curve, like a curve that is recognizable from math class, or a straight line that's recognizable from math class. Your goal is to think of the simplest, smoothest, recognizable shape that you know, pattern that you know from a math class that doesn't actually hit all the dots, but rather averages them out. Meaning, and I'm sure you've heard this before, but meaning you want to draw some sort of curve that's above about half of the dots and below the other half of the dots. Ideally, you want to draw a curve that's sort of above by the same amount, half of the dots, as it is below the other half. Now, that's hard by hand to do exactly, but you're looking for a curve that captures the dots. Now, I'm also going to work, so you're not, so it may be a straight line, it may not be, but that's your first actual conscious decision that you want to ask yourself. When you see a bunch of dots, the first thing to ask yourself is, do you think they fall in a straight line? When they do, that's great, and sometimes they do, but do not assume that they do just because you want to. To be honest, especially to help you with lab 2, I'm telling you right now that a lot of experiments we do, when we collect the data, if we don't think about 0,0, if we don't have a lot of data points, and we collect like 4 or 5 data points, a lot of data can fall into what looks like a straight line. And especially if we're sort of wanting things to be straight, we can easily imagine a straight line connecting the dot. Trending the dots. But if we consciously think about 0,0, and if we recognize that that is a data point too, then we can often see that our dots are not falling in a straight line. And in fact, that's a hint to anybody who's still paying attention to me in this dreadfully boring lecture. If you're listening to me right now, I'm telling you right now, that's a hint for lab 2, is that you're going to, at least for part of lab 2, you're going to get a bunch of data that may well look straight, but it ain't straight. if you include 0,0. I'm just saying, if you heard that, and I'll move on. So you're looking to draw some sort of smooth curve that averages out your dots. And when I say smooth and simple, again, I mean, it may be curved, it may be straight, but if it is curved, then you want to ask yourself, do I recognize this curve? Is it like a parabola, like y equals x squared? Is it a parabola, like y equals negative x squared? Is it part of a cosine? You want to ask yourself that. Once you draw a rough trend yourself, and once you conjecture what type of function it is, then you can put that function into Excel or Desmos. You can certainly ask Desmos or Excel to do a best fit. Many of you may know from other classes, you can always ask a graphing program to find the best fit line or the best fit curve. But the main thing I'm trying to warn everybody now, the thing that gets a lot of people into trouble is, yes, machines, computer programs, software can help us model fit or curve fit. But the way it helps us is that once you tell the computer, oh, I think this is a line. I think I know these data points aren't perfect, but I think they're falling pretty close to a line. In fact, all of them look like they really are in line, except I have this one sort of outlier that's off there and kind of off the line. But I know that was just kind of an outlier because, like, life is life. And I was drinking too much coffee when I took that data point. So it's like off. So you could say to Desmos or to Excel, oh, give me the best fit line for this data. And if you tell that, if you hit like best fit line, then what Excel's doing is it's saying to itself, okay, the user, the scientist, you are assuming that this data falls into some kind of y equals mx plus b, and Desmos is going to give you the best possible m, like it's going to give you the best possible line that most perfectly averages out those dots, and it'll tell you what m is and what b is if you told it that the data falls in a line. And that's great. And once you do that, if you believe it's falling in a line and you tell Desmos that and it gives you the M and the B for that line, good, then you've just learned something. Or like you did with Professor Liu last week, if you see all your dots and you're like, oh no, that's not falling in a straight line. I think it's falling in a curve. And oh, it kind of looks like a cosine curve, or it kind of looks like a cosine curve, or it kind of looks like a sine curve. Then you could tell Desmos, oh, okay, give me the best fit sine curve for this. And Desmos will give you the constant, the A or the B, like you were talking about with Professor Liu. It'll give you the best sine that you never could have come up with just your hand, with your brain. Yes, it can do this great work for you. But it can give you the coefficients for some function once you tell it what kind of function to try. But the computer cannot decide what kind of function to try. Only the scientist can. And that's a huge part of your job here this week, next week, is to look at your data and decide what kind of relationship you think it falls into. Is it a cosine relationship? Is it a linear relationship, i.e. directly proportional relationship? Is it a square root relationship? Your job is to get good enough data to see the basic shape. Then when you choose what you think the basic shape is from your background knowledge in math and science, then you put that shape into Desmos and it'll give you the specific values for the coefficients for that shape. And then you'll really know, and if it does that and they look good, then you'll really know, oh, okay, I think I was right. This is good. But it all sort of pivots around your conjecture for the shape. So, so I'm almost done, believe it or not. And I'll stop to see if there's questions. But what I'm saying here is, the ultimate thing that I'm saying here, sort of screaming here, is that the purpose of any physics experiment anyway is to collect a bunch of data to ultimately develop a mathematical equation, a mathematical function. Like many of us are used to thinking that in physics or in science, what we do is we solve problems by plugging into equations. Like many of us have had that experience in the past, that we get a problem or a situation, or maybe even an experiment in physics or science, and then we use equations in order to get answers. What I'm saying is, no, when we really do physics, when we're really doing physics in the lab, it's actually the other way around. Our goal in the lab is to develop those equations in the first place. They come from somewhere. So it's actually not necessarily rocket science, so to speak, to develop equations in the first place. When you go into these labs, you're not using equations, you're generating equations. And an equation is a mathematical function. An equation is some dependent variable. Some variable depends in a certain way on some independent variable. Like y equals mx plus b is a function. It's a relationship. X and y are the variables. Everything else in that equation is constants. M is a constant, b is a constant. It's often known as coefficients. What you do in the lab is you collect a bunch of data, you relate the data for one variable to the data for another variable, you relate them on a scatter plot, then you stand back from the scatter plot and ask yourself, what basic type of mathematical function does that look like? It does require some background and some experience in math. And of course, you'll get help and stuff like that. And none of the functions we ever get in this class are like crazily exotic or unusual or unseen before. I mean, they're like y equals x squared, or y equals square root of x, or y equals cosine of x, or y equals mx things. I mean, they're nothing crazy, but our job is to look at our scatter plot and decide what type of mathematical relationship or function one variable bears to the other. And then once we think we know the type, once we draw the basic shape, then we can tell that shape to graphing software and get the particular details of that shape. What do I mean by the details? I mean all the other constant values that actually specify exactly like the y-intercept of that shape, or the slope, or how the slope changes, or whatever. Those other values that get spat out by the computer are the constant coefficients. What we're telling the computer is how the two variables are related in a general way. So the computer cannot spit out to you coefficients or constant values until it knows what kind of function you think it is. It will trust you. It will give you coefficients for whatever function you tell it. So your job as the human being is to make a conjecture as to, and then test what that basic function or shape is. I'm making this probably sound harder than it is, but it is the sort of point of what we're doing there. Now let me pause for a second. Again, we're almost there, I promise. I don't know why I keep apologizing, but my job momentarily is to like sort of relate this back to what would have happened in lab 1 with F directly proportional to X. I'm going to relate it back to that, but I know this has all gotten sort of very abstract and out of nowhere, but do you sort of follow what can I just get in the chat? Do you sort of follow what I'm saying so far? Does it, or have I lost everybody I've either lost everybody to boredom or to confusion, but do you get what I'm saying so far, sort of? Yeah, okay, thank you. Woo! Thank you, Jesse. Thank you, Enrique. Thank you, Danny. Thank you, Shio. No, that's honest. And if you don't totally get it, we'll see in a minute, but you can totally tell me, but thank you. Okay, and thank you, direct chat person. Okay. And again, there's not much to get. I know it's sort of like all old news and but the large thing I'm trying to say is what you're going to do in labs, in each lab, you're going to design a way. Oh, and thank you, Vani. Okay, good. You're going to design a way. You're going to have free time, free space. You're going to have 2.5 hours to work at your own pace and stuff in order to figure out whether a certain statement or a set of statements is true or false. And those statements will be put on the board. Okay. This week, what it would have been So for what would be lab one, what you would have done, or what we're talking about right now, is you would have given this equipment, you would have set up a table of values of X and F. You would have tested a bunch of different X's. Like you would have tested, like stretch the spring out to 10 centimeters, stretch the spring out to 20 centimeters, stretch to 30. And for each one, measure the restoring force exerted by the spring. And you would have made this table of values. Then you would make a scatter plot from your 2-column table of values. You'd have like 5 or 6 dots on your scatter plot. You'd ask yourself whether you thought 0, 0 is a dot on your scatter plot. And your key question you'd be asking yourself is, do you think, for this case, you'd be asking, do you think those dots are falling in a straight line or not? Like, right, like you don't know until you get there. We're telling you what type of answer you're looking for, but we're giving you basically we're giving you a hypothesis and we're asking you to confirm or deny it. For this one, excuse me for a second. Yes, hi. I'm almost. I'm just.
It's been literal forever.
I know Wednesdays are always forever. In about a half hour, a little bit less.
No.
That's the deal. You want to say hello quickly?
No.
Okay. Well, then I've got to do this, and then I'll be done, and then we'll play. This is just the way Wednesdays are.
I will fist you.
That's nice. Thank you. Okay. Thank you. I love you too. Okay. I appreciate it. Wow, that actually hurts. Okay. Okay. I love you. I will see you very soon. The faster I can get back, the faster I can finish it. They want to go too. Believe me, they want to go play too. And so do I.
Why can't you just quit your job?
Because then we would have no money and then we couldn't afford Nintendo.
Well, we would. Mom
Yeah.
would have money, and
Well-
so do I.
Okay, well, I'll think about it. Okay. And also these people wouldn't get educated. Okay, but now I've got to get the faster I get back to this, the faster I
don't
can.
care.
I know. Okay. Okay.
Now shut your face.
Thank you. That's what they're saying too.
Because you stink.
Okay, enough. Do you want to introduce yourself properly or do you just want to say?
You're the worst.
They think so too. Do you want to say hello? Okay. Faster I do this, faster I can get back.
Magic wand.
Okay, dude.
I
Love you.
will tie you.
Okay. This is being broadcasted to all over the world right now. Okay.
You are the worst.
Thank you very much. I appreciate it. But now,
Are you
the
actually?
longer yeah, we are. And the longer we take to do this, the longer.
Wait, am I in a film
Yes.
that everyone will see?
In the whole wide world. Now, can I please get my?
Hey,
Okay.
yay!
Okay, dude.
No, go away.
No, you have to go away. The faster I get back to this, the faster I can get done. I've got to get done.
Brown.
Dude. Very nice. I'll be up soon.
I don't.
Seriously, you gotta stop. The longer we do this, the longer I'm gonna take. I've got to come. Okay. All right. So my first question that I'm actually asking you all to think about is, and I would like answers in the chat or whatever, is do we, for this case, for if we did an experiment to
Ooh, what
wait,
experiment?
stop.
What experiment?
If you're listening, I'll say it, to relate the force of the spring to the displacement of the spring. If we did that, would we expect 0, 0 to be a point? You gotta stop.
Maybe no. To know, got you. Hi.
Okay, I'm actually going to pause for a second. So I'm asking you, actually, I'm going to ask you both questions, so all to think about, and I want to see the answers in the chat. I'm going to pause for a second, as you can imagine. But this is question 1, and then question 2.
Hi. Yes, I am here. What's up? What are you looking at? No, seriously, what are you looking at? What? What are you looking at?
So here's my questions for right now. What I would love you to think about, and or if you've already thought about them, I'd love answers in the chats. And I'm going to turn off my video and mute for a second, but okay, sure, but you know what I'm saying. My two questions are: do we expect or believe 0, 0 to be a point? And second of all, given that, whether it is or it isn't, do we expect in this case, do we expect these dots to fall in a straight line? Now, there's no way you could know that if we were just walking into the lab right now. But because you've in effect been given the answer already in lecture, I think we can conjecture this. So I would love to see answer. So we're racing to the conclusion here for this one. So I'd love to see in the chat. Do we? I would love. Oh, cool.
I can't control when.
Okay. First of all, thank you, Vani, in a big way. Like I totally see answers in the chat from Vani, and they totally show that she totally understands my question. I'm not going to say whether I agree with your answer or not, because I'd like to hear from other people as well. So I'd love as many answers as possible. Or if you don't understand the question, let me know. But again, we are nearing the conclusion here. I know this has been a long day, and I know it just got longer a minute ago. That was my son, Felix. He's 7 years old. As you can tell, I love him to a fault. But I would love to hear from other people, and I can repeat the question, but Vonnie clearly understands the question, and I'd love to hear from other people too. One, are we expecting, in other words, if X is 0, do we expect F to be 0? And number two, do we, okay, so number two. Okay, no problem with the slow typing. No, this is great. Take your time. And I apologize for my slow teaching. But I've got two answers here, great answers from Vonnie and Shion. Again, they're slightly different answers, but they both certainly demonstrate that they understand the question, which I appreciate. I'm going to give more time to get a couple answers from more people. It's also possible, by the way, I didn't mean, maybe the 8 questions slightly, I'm sort of assuming because you guys were so expressive and correct on the whole sine cosine business that I kind of assumed that you felt a certain level of comfort with the F equals negative KX business, but I might have assumed too, maybe you're not. I don't know if you're as comfortable with it as I assume. We're about to find out, but that's 2 answers. I'd love 2 more answers before I say right or wrong. Or, and I'm not trying to put pressure on people. Again, I know it's a long day. Even if anybody puts in the chat, just like, I get it, but I don't know, or just to know that we're alive. Or something like, can you repeat the question? Or tell me what you're confused about. Or just say, I'm here, but my brain is dead. That's fine too, but I just kind of want to know what I'm dealing with here. We all suffer under Zoom. So I'll wait for one more response of any kind. One more response. The question again is, do we, okay, cool. Okay. Fair enough. That is honest. I appreciate it. That's a third answer. But thank you, Jesse. Okay. I'm going to answer this now. Can I just, but Vonnie said her brain is dead, but she's the one who answered. That's funny. Okay. And so bear with me. Again, I know this has been long. Again, part of my goal here, I know this is not exciting. It's just to get things calm and clear for next week. I'm going to try to address this and wrap it up. But let me ask, but those people who are not, please tell me the chat. Just tell me this. Even if you don't have an answer or if your brain is fried, do you understand the question? Can you just sort of say yes or no in the chat? If you understand the question that I'm asking. That's a lot of yeses. Okay, great. Okay. Thank you. That's very definitive. I actually didn't expect that. Okay, great. Okay, so a little bit. That's honest. That's fair. Okay. So I'll answer these 2 questions. And once I answer them, I think we'll pretty much have enough to go. I think, yes, okay. 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 So I'm reminding you, okay. No, great. Okay. Yes, Vonnie, ask the question, please. And you can use voice if you want, that'd be great, but if not, here.
Okay, yeah, I could sorry. I
No,
just
no.
have a question. For something that you just wrote here, if x is equal to 0, do we expect x to be 0 too? Like can we like refer to the formula to say
Right.
that it is,
Right.
that it
Great.
could be?
Great question. And I'm very glad you asked that because that is what's confusing. That's a perfect question. It totally shows you're paying it. Okay. So here's the deal. For right now in this discussion, yes, like right now, what we're doing is, yes, you have that formula, that equation already from Professor Liu. So right now I'm using it as an example to see how all this works. So yes, right now, yes, you can. And if you did, what would you say the answer is?
So given that it's like f is equal to negative kx, it'll be 0 on both sides if x is 0.
Absolutely. Yes, that's correct. And that is what I'm looking for right now. That's very good. Yeah. And I think that is what you put in the chat a minute ago and a couple other people. But yes, but let me say this to everybody. This is what he's a little bit confusing about right now. But yes. I mean, that's good. That's good. What I'm saying to everybody is you actually know, because you already learned from Professor Liu, that f equals negative kx. So we can use that as an example for how these things work. If you were going into the lab right now, you wouldn't know that equation going in. Like in the future, you won't know the equation going in. But what you're trying to do in the lab is establish equations. So see, today we didn't take data. We can't take data. We're not in the lab. So we don't have the data. But we actually already have the equation from Professor Liu. So in a way, like that's our information is Professor Liu's equation. So yes, first of all, given that you've already learned that f equals negative kx, that would be an example where I absolutely agree with Vonnie, and I believe if x is 0, f will be 0. Let me be more specific in English. X means how far we are from equilibrium, and F refers to how hard the spring pulls or pushes something toward equilibrium. If something is at equilibrium, I will not expect the spring to pull on it at all. The spring attempts to pull things back to equilibrium or push them. When they're there, the spring doesn't have to do anything. So in my mind, I would expect if X is 0, F is 0. And indeed, yes, that's what that equation says. When you plug in 0 for X, you get 0 for F. So first of all, in this case, so yes, Vonnie is right on both counts. So I would expect, and also I should say, it's not only Vonnie, but like to go back, I'm very pleased like, oh yeah, Vonnie was the one who said that originally, but also Shion and Jesse totally were right. So first of all, yes. F refers to how hard the spring pulls or pushes on a mass to get it back to equilibrium. Now, I wouldn't know the relationship between F and X unless either I did the lab, the experiment, or Professor Liu had told me the equation. Professor Liu apparently has told me the equation. Apparently, she said it's F equals negative KX, where K is just some constant, some number, not a variable, just some constant number. Apparently, what that equation means, well, okay, here, I'll just say. Apparently, according to Hooke's law, according to Professor Liu, and again, for this first lab, in a way, we had Professor Liu's lecture in a way, instead of us doing the data collection. But I'm here to, sort of put those two things together. So according to Hooke's law from Professor Liu, F equals negative KX, F equals negative times some number times X. What that means in English is the farther we pull the edge of the spring away, like the more centimeters we pull X to the right from equilibrium, apparently the harder the spring pulls, the harder the spring forces, the harder the spring pulls or pushes, the more newtons of force the spring exerts on the mass to bring it back toward equilibrium. Like if we pull the mass away to the right, the spring pulls on the mass toward the left. That's what the negative sign means. The negative means in the opposite direction from displacement, from that of the displacement. The negative sign means the force is a restoring force. Now, apparently, numerically, the force is equal to some negative times some constant times X. That is to say, so I'm asking this then. If the law, again, we didn't actually collect data here, but we did hear this law from Professor Liu. Given the law, F equals negative KX, my question to the class, actually, I've already asked it, and many of you have answered, do we think that if we put X on the independent axis and F on the dependent axis, do we think that we get more or less approximately a straight line? And at least 3 people gave very articulate answers in the chat. And I'll tell you this, to cut because I know I'm sort of torturing you and I don't mean to. Wait, I'm about to tell you the answer to number 2. Like the answer to number 1 is yes, I think 0, 0 would be a point. Like that would go into our data table if we were doing lab 1 right now. Number 2, I asked, do I think the data would fall in a straight line? I'm going to give you the answer and we're pretty much going to go soon. But let me ask you, now that I've said this, are people, I think Vonnie's question was very good, like, because it is a little bit confusing that we're like talking about the lab now, but we're not actually doing it. That is a little confusing. Could I just ask in the chat, can you tell me, question 2, would the points fall into a straight line? Regardless of whether you think you know the answer or not, please tell me in the chat, do you think you understand the question I'm asking? Would the FX scatter plot, would it fall into more or less a straight line? Just please tell me if you can picture what that question means. Okay, so Vonnie, I appreciate that Vonnie's totally understands and she's giving an answer, which I appreciate, but I'm not even asking the rest of you for an answer. I'm just asking to know if you know what the question is. Okay, Shion saying she understands. I said she or he, I'm sorry. But Shion understands, Enrique understands, Danny, yep, Vonnie, no, it's fine. No, it's fine, Vonnie, but I'm just saying to other people that they don't have to do that. Brianna understands, okay. Yahim, is it Jahim or Yahim? You'll tell me. Well, anyway, yes, okay. So good, you all understand? So here's the deal. I'm going to tell you the answer. And again, we're almost done. Thank you for being so patient. Here's the deal. 3 people in the room said no. I'm going to tell you right now, I think I know why they said no. And I think it's because they were paying very close attention to Professor Liu's lecture and taking it very seriously. But I think there's a mistake. I think the answer is yes. Okay. And but the fact that 3 people said no is not because they're crazy. And it's not because they're stupid at all. And it's not because they're not understanding the question. I think they said no because they totally, you'll find out in a minute, but I think they said no because they so deeply internalized a certain aspect of what Professor Liu was saying that it got misapplied here. I'll tell you what I mean. Here's what I think. I think it would be a straight line. Again, I know why people, I think I know why people said no, but let me first tell you why yes. I think these dots, in other words, the dots would more or less be in a straight line, more or less. And they would actually be, if we were doing this all properly, I think if we were taking into account negative signs, I think it would be a line going down into the negatives if we were taking into account. If not, it would be the positives. I think it would be negatives. And I think the slope would be negative k because f equals negative kx. I mean, this is like y equals mx plus b, where b would be 0. I think that what f equals negative kx means is that that you have a relationship of a constant unchanging slope. The slope is negative k because k is just a number. It's a constant number. I think what f equals negative kx, what Hooke's law means is if you pull the mass out twice as far, the spring will exert twice as much force. the reason I think I know this would be a straight line is because the law is f equals negative kx. The law is not something like f equals negative kx squared or f equals negative kx cubed, or nor is the law something like f equals cosine of x or something. The law is that it is like y equals mx plus b. Only instead of y, we have f. And instead of m, we have negative k. But I think, in other words, well, I'll say, I think it is a straight line. And the reason I think you guys thought it wasn't is because you were thinking about cosines, which means you were totally paying attention to Professor Liu. Like, you're not crazy and she's not crazy. You were thinking about cosines, but the cosines that Professor Liu was talking about and I'm not saying this to trick you guys at all. I'm doing this whole lecture today that's I know long enough to hopefully to untrick you, because tricky things are going on. So I'm trying to get this is not meant to trick you. It's meant to clarify something that is tricky. The cosines and everything that you were talking about is how the mass is moving back and forth in time. Like the mass starts here and it goes to equilibrium, and then it goes past it, and it goes to some point on the other side, and then it goes back up to equilibrium, it goes past. Like, the cosines that you guys were talking about was what this is the scatter plot that you would get if you were measuring where the mass is at every single moment in time. If you, and that will become very important in this class. That wasn't a waste of your time. That wasn't a distraction. That wasn't like a bait and switch. If we were ever thinking about if we ever took data on for every single moment, if there was a mass going back and forth on a spring and we took data on every single moment in time where it is, I think we would get something that looks like a cosine graph. In this first lab, and that's all because f equals negative kx. But in the very first lab, if we were just studying what force is doing as a function of x, in other words, if we were studying force as the dependent variable and position as the independent variable, then I think what Hooke's law says is we get a straight line. If we were studying position as the dependent variable and time as the independent variable, then we would get that curvy cosine. What really, really matters, what we always want to be straight in lab, in experimental design, is what is our dependent variable and what is our independent variable. Again, I'm not trying to trick you. I'm trying to straighten out a potential confusion or a potential trick. The thing I'm trying to say ultimately is, we'll know that we're all cool and clear on this and about to go. If you believe me for a moment, if it's sort of making sense now, and even if you made a mistake before, no shame, no blame. I'm just trying to get straight. And again, I really appreciate that 3 people really did try to make an answer to this question. And the fact that all 3 of them said the same thing, I think it's not because they were crazy. I think it's because they were really paying attention, really. But there is like a confusing thing going on here. So it's not their fault or something. But what I'm saying now is, if we recognize what I'm trying to say, if we understand that f equals negative kx is a straight line on an fx scatter plot or on an fx graph, then let me ask, this is my final thing. And if anybody, I can imagine people may not want to step up now, but then if I'm saying f equals negative kx is a straight line, which I am saying, then, and if you knew that somehow, either because of Professor Liu or me, or because you did do a scatter plot and stuff and found that, then what do you say to the ultimate question? The ultimate question that would have been the ultimate question of lab 1, the thing that would be on the board, is f directly proportional to x, true or false, yes or no? If I am saying that the fx graph is a straight line graph, then do you say that f, like if the ultimate question here of the lab is true or false, f is directly proportional to x, do we say true or do we say false? I've lost every, oh, Yes, yes, yes. Yeah, good. Yes, awesome, awesome. For a second, I thought I lost the whole world, but it looks like I didn't. Yes, yes, Vani. Yes, Amaya. Yes, Brianna. Yes, Jahara. I think that's right. Yes, Jesse. Yes, Shion, if I'm saying that right. And listen, even if you were tentative, or even if you're scared because something else was wrong a few minutes ago, or you're scared of my son, or whatever, or you're just like, your brain is fried, and so is mine. Like, even if you were tentative, if in your heart you feel like the answer is yes to that, good. Even if it took us all this time to get to that, good. Like, I agree. The answer is true. Like so if we were doing lab, so we've now done lab 1 together. As far as I'm concerned, like I am ultimately saying, our conclusion for the first week is that on a spring, or in a spring, the restoring force exerted by a spring is directly proportional to displacement. If we had done the lab, we would hopefully have found that out because our scatter plots were straight lines. Turns out we actually sort of found it out because Professor Liu lectured the law, like she gave us the law, and now we have it, that F equals negative KX. But I'm saying the meaning of that law, the implication of that law, is that what it's saying is that restoring force exerted by a spring is directly proportional to the displacement of that spring from equilibrium. That's what I'm saying. That would be our first, that's the first truth we've established in this class now as of lab 1. And I'm saying lab 2, you're going to come in and a very similar thing's going to happen. A relationship is going to be put on the board, a direct proportionality relationship, actually 2 of them. It's going to be like, it's going to involve springs, just like this. It's going to involve slightly different variables. You have to be careful. Like, it won't be the same variables, but it'll be variables. You'll have to test them, get a column of data. You'll get a scatter plot. If the question is asking, which it will be, is blah directly proportional to blah, your main first goal is to find out whether the scatter plot falls in a straight line. If it falls in a straight line, then the answer is yes, they're directly proportional. If it doesn't fall into a straight line, then they're not directly proportional. But then you'll have to, but then you'll go one step further. Like, I'll tell you right now, one of the relationships you'll get will have some, it will be like, is this related to this squared? So you'll have to see, is your scatter plot look like a parabola or not? That's what's going to happen in the second lab. And again, it's going to be about springs. It's going to relate position and time and stuff like that. It'll be a little bit bigger than this, but that's how it works. And from here on in, every lab is like that. You'll get used to it. It'll be less annoying when it's not on Zoom. And the last thing I'll say is that each fact or truth or whatever that we try to establish in lab, they all build on themselves. We'll talk to you more about this next week, but or in future weeks. But each lab has a conclusion that we'll learn by the end of that lab. And as we step from one conclusion to the next, we're trying ultimately to get to a question about the whole universe that we'll be able to answer if we logically put together all of these lab conclusions. Okay, I said you could go, I would like, it's not, I know we've gone to the whole, almost the whole end of the period, but technically we'd still have 20 minutes. So I'm happy. Let me does it make sense? Do you feel somewhat ready to walk into the lab next week? I mean, I know you're a little bit overwhelmed now or a little bit tired, but do you feel like, can you imagine if you got 6 nights of sleep now or whatever, can you imagine walking into the lab next week and will you sort of have an idea of what's going on? Do you think, do you sort of just let me know in the chat? Are we good? I mean, I'm good to go if you're good to go, but yes. Okay. That's good. Okay. Okay. Cool. Great. I will take, great. Thank you. Okay. And I know you've been very, very patient. You're being very flexible. You're also clearly very smart. And again, if the one thing that you got, I really do think that I think you were clearly paying attention. You're obviously were paying attention to lecture, which is great. And so now I think we're set for lab. So oh yes, please do. Oh, thank you, Enrique. Wait, sorry. You should totally, not with me, but yes, you should totally make a Discord server or something. That would be and of course, and I'll pause for a second if you need a second to do it. Yeah. well, a lot of times people do Discord. I don't know if that, oh, yeah, in a lot of physics classes make Discord servers. In fact, some of our, so yeah, and if you want to take a second to use this forum to do that, I mean, and it's for you, not for me. I mean, but sure, if someone wants to just set it up and I won't leave until you, I think that would be very useful for all of you. And we will make lab groups and stuff as well, but yeah. So I'm just gonna hang out for a second for you to do that or whatever. And I'll hang out if there's any questions, but also remember the PDF of all this will be posted. In fact, right. Okay, I will shut up. I'll turn away. I'm going to post this PDF of notes to you all right now. And then also please remember that in a few hours or in like a night, the recording of this whole thing will be uploaded to YouTube. And then that link to YouTube will be posted in your Google Classroom. So all this. Or what's it people use what's up to. Okay, this is none of my business, but I definitely think you should do this. And I will sit here so that you can use this, at least use the chat to set it up. I think that would be very useful. And while you're doing it, I will post this PDF.